Hi, it's Tim and welcome to the channel. Today we are back with the Plus 4, or rather more specifically we are with the Plus 4 power supply. And what we're going to do today is take these things and a fuse, put them in this box and make a new custom power supply. So let's do it. So we have tested this power supply before and we do know that it works, but the big problem with these power supplies is that they fail, and they fail in a particularly bad way, in that they fail by short-circuiting on the 5 volts, the input and the output of the voltage regulator. And what that does is basically puts 10 volts onto the 5 volt rail, and everything that it's connected to will go bang, or at least so long term this is not a good power supply to have, because if it has not failed, it's going to fail at some point. You can get little what they call power savers that are basically a triac sort of crowbar circuit that will limit the current that can go through, or at least limit the voltage that it will go up to. But I'm not going to do that. What I'm going to do is I'm going to take the cables off this and then apply it to this, and we'll come on to that in a moment. I'd like to thank PCBWay for sponsoring this video. PCBWay make excellent quality printed circuit boards, just like these. These are circuit boards that I've designed myself, submitted the Gerber files. PCBWay have made them, $5 for 10 boards. They also do shared projects, just like this or like this. They also do CNC machining, 3D printing, flexible PCBs, PCB assembly. PCBWay are running their 6th annual design competition. If you want to design a circuit, then you can submit it and you can win big prizes. Check them out, www.pcbway.com. Let's just quickly go through what is in this power supply. You can see that it's a 4-pin connector. And what we've got, that's basically our plug, and then these two wires are 9 volts AC, and these two wires 0 volts and 5 volts, so this is DC. So that's what the Plus 4 is expecting. Now this is for a Plus 4 with the square connector, and it works exactly the same if you want to build a C64 power supply, or if you want to build a C128 power supply. You can use exactly the same components, you can do exactly the same. The only thing different is going to be the connector. And so let me illustrate that. So for a C64 we have basically that is our C64 plug. In exactly the same way, we've got 9 volts and 5 volts DC. So that pin and that pin are 9 volts AC, and that pin is ground, and that pin is 5 volts. Sometimes this pin is also 5 volts, but not always. Sometimes that's not connected. And for a C128, which is superficially similar to the Plus 4, but actually totally different, this is a 5-pin plug. That's C64, that's Plus 4. And what we've got is totally different. So the 9 volts AC is actually those two, and then the 5 volts DC is actually that and that. So totally different plug, but you could build this power supply with any of these 3 plugs on it. Or you could build it with some sort of adapter so that you can plug in a different lead according to which computer you're using. Choice is up to you. The reason that I'm building a +4 specific one is because these leads are actually quite rare. And although I could convert the +4 to use a C64 power supply, I don't really want to. There will be other +4s and they will use one of these. So building a proper +4 power supply seems like a good idea. I can do another one later on and make it a C64 power supply. That would be fine. So we've got a transformer that is giving us 9 volts AC, and that is then also rectified and goes through a 7805 and is converted down to 5 volts. When this fails, it basically does that, and that is not what we want. So what we are going to do we've got various odd little bits, like there's a fuse and a piece of Veriboard. That's just purely to mount the bits on. So what we have here is, this is a 9 volt transformer. So 230 volts input, or 240 volts as it really is. And then there are 2 sets of output windings, and each one is 9 volts at 0.75 amps. So we can wire those together to get us 9 volts at 1.5 amps. And that's what we're going to do, because we need 1.5 amps. So power supply, or a transformer. And then we have, I'm not sure at the moment whether to use this or this. They are essentially the same thing. This is a little bit of a better fit. This is a Meanwell power supply, and it gives us 5 volts at 3 amps, which is plenty. This is more than this gives. This gives us 9 volts at 1 amp, so 1.5 is going to be better, and 5 volts at 1.5 amps. So this gives us 5 volts at 3 amps, either this one or this one. This has the advantage, it's got little vertical plugs, whereas this needs to be wired with screw terminals. And I think we might have trouble fitting this in the space available. So we might not use that one, we might use this one instead. And I've got some connectors that will go on that. It's not a problem. So basically what we're going to do is mount these on here like this. Somehow go on there. And that will go on there like that. And then this will go in here. Like that, or more probably like that. This is a 3D printed case. You'll notice that I've actually printed a separate Commodore logo in what they call transparent PLA, and that's just been glued into the bottom. I've pre-done that. It's a little bit crude on the inside, but it will do the job. You can download this from Thingiverse. I've made some slight modifications in that I've put some vents in the side. They were not in the original model, and I've made a hole for the fuse. If we do this, it's not going to fit sideways, and it's also probably not going to fit lengthways. Let's try that. Goes in there like that. Maybe, but it's very tight. And it's also going to interfere with the cable coming in unless we do it round this way, in which case we've got to screw the terminals in before we put that on the board. There are holes in the bottom which we can use to screw it down, or at least one hole that we can use to screw it down. I think on balance I'm going to go for this one. It can go that way round. There's plenty of space. We can just fix it down either maybe with some cable ties, or possibly I'll put a screw in there. So let's take the cables off this. I don't want to just cut it because I want to keep these grommets, because we can use these grommets on this. You'll need a new plug, by the way. That's very old and it's not code because it doesn't have insulators on the bottoms of these pins. So let's just decide what we're doing. This transformer has one input winding, which is our 240 volts, and it has two output windings, both of which are 9 volts. And we can see that on the transformer. 9 volts 0.75, 9 volts 0.75, so that's the input. These are the two output windings. And we want 9 volts at 1.5 amps, so we need to join these two together. And the way we do that is we connect that to that, we connect that to that, and that gives us 9 volts 1.5 amps. And then we're going to take our feed off this, and that's going to go into our mean well. That's the input voltage, which is the wide space, and this is the output voltage. So that's our mean well. And this one is actually 2.8 amps, whereas this one is 3 amps. The difference is not significant as far as we're concerned. So that's what we're going to do. Now let's see if we can break open this power supply. I don't quite know how we're going to do it. I'm going to try levering it with a screwdriver. Maybe 2 screwdrivers. There we go. This is the PCB for the 5 volts, and you can see it's remarkably simple. In theory it's possible to get this potting compound out. You can see the base was really only wedged in. I don't think we even broke anything. But by application of a hammer and some pieces of wood, we can actually get this out and then reuse the case for another power supply. But I don't think I'm going to do that. We may as well just cut these wires off. Okay, that's the main side. So yeah, this is basically, it's not repairable because the voltage regulator is actually embedded in the potting compound. And the consequence of that is if it goes, then you can't repair it. I mean, it's sort of understandable you'd do that with the transformer because that will stop it humming and whatever. It just adds to the weight though. So after all that, the holes in here are not big enough. One thing I could do is just feed it through and put a cable tie on the inside of that, just to stop to act as a sort of What I was planning to do with this, just by the by, is to put an LED on that so that it lights up. I put that on the wrong bloody side, didn't I? Oh no. I can do the same with that, I think. Cable ties will act as a sort of makeshift grommet. That requires the plastic to be too thin. Okay. So I needn't have worried about getting that open. Now, colour coding, red, blue is the 5 volts, yellow and white is the 9 volts. And we can double check that. Let's just beep it. So 5 volts is down at the bottom. There we go. And so this must be 9 volts, and this is blue and brown. Of course we know what that is. That is our regular mains. So let's think how we're going to do this. Okay, so I've cut the holes in the PCB and made a barrier there between the mains and the low volts. And what I'm going to do is I'm going to use one of these little screw terminals. Oh, I've also put the fuse holder in there. So that's going to go in this way round. Plenty of space to clear. Then what I'll do is I'll put these here, and that will be the mains terminal for this. I'm just going to hold that down with a bit of tape, like that, and then I can solder this down. Then I'm going to put another one of these on this side, like that. That's actually offset. And that's going to be the output. So what I'm going to do with this is, because this is really just regular mains cable, so I'm going to cut off a length of that. It's probably enough. Now one of those is going to go to the input of the fuse. It's going to be the live wire. So the heat shrink will go on there. Let's just tin that. Okay, so there is our fuse input, and what I'm going to do is I'm going to get some of this, tin that, and that is going to be our fuse output. We won't forget to put the heat shrink on it. There we go. We will sort those out in a little bit. In fact, we want that to be somewhat shorter. Again. Right. Now those will go into there. We'll put 2 more wires from there into this. So what I'm going to do is I'm just going to cable tie this down. That way we don't have to worry about finding screws to fit. A little bit further on, I've crimped these cables into these connectors so this can go onto here. Like that. And these will go into that output. And I've crimped another connector onto here. And this will go into the output. And that's the red and the blue 5 volts output. And you'll notice I've got these 2 extra wires coming off. These are going to be for the LED that I'm going to stick onto there. And these are the output for the 9 volts which are going to go off here. So let's just strip these. It's AC, so it doesn't matter which way around they go. Now what I haven't done yet is wired up the output of the transformer. So let's do that next. Now the output of this transformer we wire up in parallel. So this is 20 gauge wire. It should be good enough for 1.5 amps, but I'm going to wire it up in parallel. So it should only carry 3/4 of an amp per. I'm using white and yellow wire because the white and yellow wires are what is in the output cable. Okay, so that's the white wires connected. There we go. So each output winding is connected in parallel and they go to this. And it's important not to get the phases wrong because that would not work properly. So what we can now do is wire up the inputs. After all that, the heat shrink fell off, and it's this one as well. Let's do that again. Okay, so before we go any further, we should really heat shrink those pieces of tubing. So let me set up the heat shrink gun. Okay, that's done. The next thing that we want to do is take the fuse out of here, because we can use this waste not want not in here. There we go. The next thing to look at is an LED to go into this position here, and I think a nice blue colour. So I've got some blue LEDs. And we're going to want a resistor to go with this, and again some more heat shrink. And then this is going to stick in there like that, and that hopefully is going to show a nice blue light. Before we do that, we are going to want to test it. So let's set the meter up. Plug that in. Okay, ready to switch it on. 3, 2, 1. Nothing went bang. So let us measure. Set that to AC. Let's just check we've got 13.5 volts. That's about right. .246 DC, 5.09, so 5.1. Okay, that is about right. The nominal voltage for a +4 is 5.2. Once again, that measures 13.6 with no load on, of course. So let's hook up the LED. Now remember, we're going to need a series resistor for this. So we want something in the region of, we can try some different values to see what looks good for brightness. So I'm going to try a 470 ohm resistor, and we'll see how we get on with that. First, we can put the negative connection on. Don't forget the heat shrink. Now the flat on the case is negative. It's there, and it's usually the short pin. Okay, I haven't heat shrinked it yet, I've soldered this up. There is a 470 ohm resistor attached. So let's just power it up and check that the light works. There we go. That's a suitable brightness, and then if we put it behind the Commodore side, that is going to work nicely. Turn this off and we'll see from the LED just how long it takes for the power to drain away. Still got voltage, and there it goes. So you only need about 100 degrees or so to shrink the heat shrink. There it goes, it's done. So in order to fix it onto here, what I'm going to do is just put some epoxy in and basically stick that down. Okay, I've left it a few hours for the epoxy to dry off and set. That is definitely set. And so before I close it up, I've also screwed down the PCB onto the base. Before I close it up, let's do a final test of the supply. So I've put the output into a little vise, and so just to make it easier to measure, a couple of bits of heat shrink that I can stick onto the pins so that nothing gets shorted out. There we go. Turn the meter on. AC volts. Power supply on. The blue light comes on. I'll show you what that looks like. It's not bad. I think next time I'll move the LED a bit further back because it's not lighting up this bottom bit. But for a first attempt, I think that's okay. So let's measure this. 13.6, that's okay, I guess. DC, now this side is 0 volts, this side is plus volts, so swap the probes around. Oops. Actually make contact, 5.19, that is correct, so yeah. 5.2 volts is the nominal output, which we adjusted. So I can go ahead and close it up and we can give it a try. So here we are, we've gone from this suspiciously heavy and slightly electrically dubious original power supply to this, which is nice, lightweight, fully modern switch mode. And that weighs something like 1.2 kilograms, which is what, 2.5 pounds, something like that. And this weighs just 350 grams. So heavy, light. This is almost about a quarter of the weight of that. And so the moment of truth. Let's try it out. You can see we have a working computer. Now that is awesome. What I don't have at the moment is the means to run any software on this. I've got my trusty, where is it, SD to IEC, but of course it goes into this style of power switch for the 5 volts to the cassette port. So I need to get an adapter for this to run off the kind of 5 volts that this can supply, or we need a 1551. Funny I should say that. More anon. So thank you for watching. If you've got this far, please like and subscribe. Check out my Patreon. I'd love to have you there. You can get early access to all these videos. There are even going to be Patreon specials that will not appear on the main channel. So check that out. It's well worth the effort. You'll be supporting this channel and I will be eternally grateful. So thank you very much. Thank you to my existing patrons. Their names are scrolling up or along or something. Please check out my other videos and I'll see you next time. See ya. Bye.